Ever wondered how microchips, the heart of our digital world, are made? These tiny yet powerful pieces of technology are everywhere around us, from our smartphones and computers to our cars and kitchen appliances. They're the engines that power our digital world, the magic behind the screens that keep us connected, informed, and entertained. Now you might think that these minuscule marvels of modern engineering are churned out swiftly and in astronomical quantities. And you'd be right, to an extent. But the truth is, creating a microchip is a complex, meticulous process that can take up to 3 months from start to finish. Just imagine 3 whole months to create something smaller than a fingernail. Speaking of size, you'd be amazed to know just how much can be packed into such a small area. Picture this. Tens of millions of transistors, the basic building blocks of a microchip, can be squeezed into a space the size of a fingernail. But why are these microchips made from silicon, you might ask? Well, silicon is the second most abundant element on Earth, and its semiconductor properties make it ideal for controlling electrical current. But it's not just any silicon that's used. The silicon used in microchips is ultra-pure, and usually shaped into circular wafers with a typical diameter of about 12 inches. In the world of microchip manufacturing, cleanliness is next to godliness. The production process takes place in an environment that's more sterile than an operating room to prevent any contaminants from ruining the intricate designs on the silicon wafer. The journey of a microchip begins with a process called deposition. This is the first step where layers of different materials are deposited onto the silicon wafer. Then, through a process called lithography, the chip's blueprint is transferred onto the wafer, and the electrical conductivity of different parts of the chip is altered through a process known as doping. Intrigued? Then dive deep with us into the fascinating world of microchip manufacturing. Why silicon, you ask? Let's uncover the reasons. Silicon is the second most abundant element on Earth, right after oxygen. But that's not the only reason why it's the star player in microchip production. Silicon is a semiconductor, meaning it can either conduct or insulate electricity, depending on the conditions. This makes it the perfect material for creating the minuscule electronic switches that govern the flow of electricity inside our chips. But not just any silicon will do. For microchip manufacturing we need ultra-pure silicon, and the process to create it is quite fascinating. It begins with sand, which is primarily made of silicon dioxide. Through a process known as reduction, the oxygen is stripped away, leaving us with raw silicon. This is then distilled in a complex process called the Siemens process, which further refines the silicon until it reaches a purity of 99.9999999%. That's right, 9 nines after the decimal point. This level of purity is crucial because even the tiniest impurity can disrupt a microchip's function. Now this ultra-pure silicon doesn't stay as a lump, it's melted down and then carefully resolidified into a large, cylindrical crystal of silicon, known as a boule. This boule is then sliced into thin, flat wafers. And how big are these wafers? Well, the typical diameter of a silicon wafer can range from just an inch to a whopping 300 millimeters, which is about the size of a large dinner plate. The larger the wafer, the more chips can be produced from it, leading to greater efficiency and lower costs. So, you see, silicon is more than just beach sand or shiny crystals. It's the foundation of our digital age, the starting point for every microchip that powers our computers, smartphones, and countless other devices. So, it's clear that without silicon, our digital world might look very different. Ever heard of a microchip surgery? Just as surgeons need a sterile environment to operate, so do microchips. In the world of microchip production, even the tiniest speck of dust can wreak havoc, causing defects that render a chip useless. That's why these tiny tech marvels are born in super clean rooms, where air is filtered and workers wear suits that wouldn't look out of place in a sci-fi movie. Now let's delve into the first step of the microchip production process: deposition. This is where layers of various materials are applied onto the silicon wafer. Think of it as painting a masterpiece, but instead of paint, we use materials like silicon dioxide, silicon nitride, and metals. Each layer serves a specific purpose, from insulation to conduction, and is only a few atoms thick. It's a delicate dance of chemistry and physics, setting the stage for the intricate patterns to follow. Indeed, cleanliness isn't just for hospitals, it's crucial for microchips too. Now let's get into the nitty-gritty. Ever heard of lithography and doping? Lithography, in the context of microchip production, is not about creating beautiful prints or engravings. It's a process used to transfer the chip's blueprint onto the wafer. Think of it as an advanced version of an overhead projector, where a pattern is projected onto a surface. But instead of light and transparencies, we're using ultraviolet light and a mask. The mask, which holds the chip's blueprint, is aligned with the silicon wafer. When the ultraviolet light shines through the mask onto the wafer, it etches the blueprint onto the wafer's surface. This process is repeated multiple times, layer by layer, to build up the complex structures within a microchip. Now, on to doping. No, it's not about competitive sports and performance-enhancing substances. Doping in microchip manufacturing is a process that alters the electrical conductivity of specific parts of the chip. This is achieved by introducing small amounts, or doses, of various impurities into the silicon. These impurities, or dopants, can be elements like phosphorus or boron. When introduced, they change the way the silicon conducts electricity, creating areas that either have an excess or a lack of electrons. This manipulation of electrical conductivity is crucial in the creation of transistors, the tiny switches that form the fundamental building blocks of a microchip. By carefully controlling where and how much doping occurs, manufacturers can design and create the complex electrical circuits that give life to our digital devices. So, lithography and doping, two processes that might sound complicated but are at the very heart of creating the microchips that power our world. These processes are as intricate as they sound, aren't they? From a wafer to individual chips. How does that happen? Now that's a question that's bound to pique your curiosity. Well, let's dive right into it. As we've seen, the individual chips are etched into the silicon wafer through a process called lithography. But how do we get from that wafer to the individual chips that end up in our devices? The answer is relatively straightforward: sawing. Sawing is the process of slicing the wafer into individual chips, also known as dies. This is done using a diamond saw, a tool that's as precise as it is powerful. The wafer, marked with the blueprint of hundreds or even thousands of chips, is carefully cut along these outlines to separate each chip. It's a delicate process, as the saw has to cut through silicon, which is hard yet brittle. Too much force, and the chip can shatter; too little, and it won't separate properly. But what's inside these chips that makes them so special? Well, each microchip is a complex system of millions, sometimes billions of transistors. These transistors are the building blocks of digital logic, the ones and zeros that make up every piece of digital information. There are two main types of transistors in a microchip: N-type, which are negatively charged, and P-type, which are positively charged. These transistors are arranged in a specific pattern to create an integrated circuit, which can perform a wide array of functions, from simple tasks like basic calculations to complex operations like rendering graphics. In addition to transistors, microchips also contain capacitors and resistors. Capacitors store and release electrical energy, while resistors control the flow of electricity. Combined with the transistors, these components allow the microchip to perform its designated functions, whether that's powering your smartphone, running your computer, or even controlling your microwave. And voila! From a single wafer we have numerous individual chips. Each one of these tiny pieces of silicon is a marvel of modern engineering, capable of performing millions of calculations per second, and they all start their journey from a single thin wafer. How many transistors can you pack into a fingernail-sized area? You'd be surprised. Let's dive into the world of microchips and marvel at the power of miniaturization. Picture a grain of rice. Now, imagine trying to fit a city's population into it. Sounds impossible, right? But in the realm of microchips, we're doing something very similar. A single square millimeter of a microchip, about the size of a grain of sand, can house over 100 million transistors. That's more than the population of most countries, all packed into a space no bigger than a speck of dust. Now let's take it a step further. Consider the high-end graphics cards that fuel our gaming rigs and power-hungry workstations. These pieces of cutting-edge technology contain billions of transistors. In fact, some of the most advanced graphics cards can boast over 50 billion transistors. That's almost 7 times the global human population, all in a piece of silicon smaller than your palm. What makes this possible is the continuous shrinking of transistor size. In the early days of computer chips, transistors were large, at least by today's standards, but as technology advanced, we've been able to make them smaller and smaller. Today we're producing transistors that are just a few nanometers wide. For scale, a nanometer is 1 billionth of a meter. It would take over 30,000 of these transistors lined up end to end to match the width of a single human hair. This relentless drive towards miniaturization has exponentially increased the power of our devices. More transistors mean more processing power, enabling our gadgets to perform complex tasks faster than ever before. It's the cornerstone of Moore's law, the prediction that the number of transistors on a chip doubles approximately every 2 years, leading to exponential growth in computing power. Incredible, isn't it? Such power in such a tiny space. It's a testament to human ingenuity and the power of technology, showing us that sometimes the smallest things can hold the greatest power. So, how long does it take to make a microchip after all, you might ask? Well, as we've learned, the process is complex and meticulous. It can take anywhere from 6 to 8 weeks to produce a single microchip, from the creation of ultra-pure silicon to the final packaging of the chip. And let's not forget the sheer density of these tiny marvels. It's mind-boggling to think that millions of transistors, the building blocks of microchips, can fit into an area no bigger than your fingernail. Yet, this is the reality of our modern digital world. Silicon, the primary material in microchips, isn't chosen by accident. Its semiconducting properties, abundance and ability to form an insulating oxide layer make it an ideal candidate for microchip production. The silicon wafers used in this process typically have a diameter of about 12 inches, although sizes can vary. The production of microchips is a delicate procedure that requires sterile conditions. Any speck of dust could potentially ruin an entire wafer. The first step in this process, deposition, involves layering materials onto the silicon wafer. These layers form the basic components of the microchip. The blueprint of the microchip is then transferred onto the wafer through a process called lithography. The electrical conductivity of specific chip parts is then altered through doping to create various electronic components. Individual chips are finally separated from the wafer through a process called sawing. The power of miniaturization has led to remarkable advancements in microchip technology. Today, high-end graphics cards can contain billions of transistors, and the smallest transistors are now only a few nanometers in size. We hope this journey into the world of microchips has offered you some fascinating insights. There's always more to learn and discover, so why stop here? If you enjoyed this journey into the world of microchips, make sure you subscribe today for more fascinating insights. Until next time.